This video begins Chapter 5 about probability and Section 5.1 about randomness, probability, and simulation. So something that has to do with probability that you're very familiar with is tossing coins. So when you toss a coin, there are only two possible outcomes. You can have heads or you can have tails. So the figure below, figure 5.1, the first one, shows the results of tossing a coin 20 times. For each number of tosses, 1 to 20, we have plotted the proportion of those tosses that gave a head. You can see the proportion of heads start at 0 on the first toss, rise to 0.5, and then the second toss gives a heads, then falls to 0.33, 0.25, 0.2, as we get 3 more tails. After that, the proportion of heads begins to increase, rising well above 0.5 before it decreases again. Suppose we keep tossing the coin until we have made 500 tosses. Figure 5.1b, which is the second figure, shows the results. So again, you see this kind of variability at the beginning, and then it kind of starts to even out here. So the proportion of tosses that produce heads is quite variable at first. That's this jumpy area. But as we make more and more tosses, the proportion of heads gets close to 0.5 and it stays there. So the definition of probability says that any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. The law of large numbers states that if we observe more and more repetitions of any chance process, the proportion of times that a single specific outcome occurs approaches a single value. So, if we go back to the example that we were just discussing, figure 5.1b would be an example of the law of large numbers, because you kind of start out kind of shaky here, but then you kind of even out at 0.5. So another example has to do with life insurance. How do insurance companies decide how much to charge for life insurance? We can't predict whether a particular person will die in the next year. But the National Center for Health Statistics says that the proportion of men aged 20 to 24 who will die in any 1 year is 0.0015. This is the probability that a randomly selected young man will die next year. For women that age, the probability of death is about 0.0005. If an insurance company sells more policy to people aged 20 to 24, it knows it will have to pay off next year on about 0.15% of the policies sold to men and on about 0.05% of the policies sold to women. So they got these percentages by moving the decimal obviously 2 places to the right, and so we would get 0.15 for men, and if we did that for women, we would get 0.05. Therefore, the company will charge about 3 times more to insure a man because the probability of having to pay out is 3 times higher. So we see that for men it was 0.15, for women it was 0.05. That's how they came up with 3 times higher. Check your understanding. On number 1, it says, according to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Explain what probability 0.61 means in this setting. So a probability of 0.61 would mean that approximately 61% of the randomly selected U.S. adults eat breakfast. For 1b, it says, why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? So although it is true that you could have a random sample of 100 U.S. adults and that 61 of them would usually eat breakfast, this isn't like a for sure definite this is always going to happen thing. So each sample is going to be variable. And so your numbers are not going to always come out to be exactly 61, but you would probably see that they're kind of close to 61 and in some kind of way. 2 says probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Be prepared to defend your answer. So your choices here are 0, 0.01, 0.3, 0.6, 0.99, and 1. So for A, it says this outcome is impossible. It can never occur. So of our choices here, the one that is impossible and can never occur is 0. Because if you have an option that can occur 0 times, then you would have a 0% probability that it would happen. An example of that would be like if you had a 6-sided die and the sides were all numbered 1 to 6, but you rolled an 8. That's not possible if you just have one die that only has 6 sides and goes from 1 to 6. B says this outcome is certain. It will occur on every trial. The probability that an outcome is certain and will occur on every trial would be 1. So this would be like, what is the probability that whenever you roll a 6-sided die with sides 1 to 6 that you would land on a number 1 to 6? So that means that every single time that I roll a die, that I would have a chance of rolling on a 1, a 2, a 3, a 4, or 5, or 6. C says this outcome is very unlikely, but it will occur once in a while in a long sequence of trials. So if an outcome is very unlikely, it would be like a 0.01. And so that would translate to be about 1%. So it would be that like it could happen, but not a whole lot of times that will happen. D, this outcome will occur more often than not. So if something is going to occur more often than not, then that would mean that it would occur more than 50% of the time. And so we can eliminate, we've already taken care of 0 and 0.01 and 1. We can eliminate 0.3 because it's less than 0.5, so we would be down to 0.6 and 0.99. The wording of the question says that it will occur more often than not, but that it's not like pretty certain to occur. So for that one, your best choice would be 0.6 because that would translate to about 60%. And so obviously 60% is more than 50%, but it's not like it's a definite for sure thing going to happen. So let's talk about what looks random. So say that you toss a coin 6 times and you record heads as H and tails as T on each toss. Which of the following outcomes is more probable? So if you think about it, you have a 1/2 chance of flipping and getting a heads, and you have a 1/2 chance of flipping and getting a tails. So if we look at each of these possible outcomes, you have on the first one, you've got 3 H's, and you also have 3 T's. And on the second one, you have 3 H's, and you also have 3 T's. So if you're thinking about which one is more probable, almost everybody usually says that the first outcome, the HTHTTH, is more probable because it looks a lot more random than if you have 3 tails in a row and then 3 heads in a row. But in fact, they're both actually equally likely to happen. So the chance that you get heads and the chance that you get tails are equally probable. Only about half of says that only about half of a very long sequence of tosses will be heads. It doesn't say that the heads and tails must come out to be closely alternating in the short run. The coin has no memory, so it's not like it's going to record and say that you for sure like can't have them repeating. And so it doesn't know what the past outcomes were, and so it can't create a balanced sequence. So it doesn't have to be random like this. It doesn't have to be perfect like this. It can just happen however it happens. Is there such a thing as a hot hand in basketball? Belief that runs most result from something other than just chance influences behavior. If a basketball player makes several consecutive shots, both the fans and her teammates believe that she has a hot hand and is more likely to make the next shot. However, this is wrong. Careful study has shown that the runs of baskets made or missed are no more frequent in basketball than they would be expected if each shot is independent of the player's previous shots. If a player makes half her shots in the long run, her made shots and missed shots behave just like coin tosses, and that means that the run of makes and misses are more common than our intuition expects. The law of averages says that the belief that the next outcome must make up for an imbalance in the past outcomes. Aren't we due for a boy? Belief in this phony law of averages can lead to serious consequences. A few years ago, an advice columnist published a letter from a distraught mother of 8 girls. It seems that she and her husband had planned to limit their family to 4 children. When all 4 were girls, they tried again and again and again. After 7 straight girls, even her doctor had assured her that the law of averages was in our favor 100 to 1. Unfortunately, for this couple, having children is like tossing coins. 8 girls in a row is highly unlikely, but once 7 girls have been born, it is not at all unlikely that the next child will be a girl, and it was. Simulation. Simulation is the imitation of chance behavior based on a model that accurately reflects the situation. So when you are performing a simulation, the first thing you need to do is state what you're doing. So what is the question of interest about some chance process? The next step is to plan. So you describe how to use a chance device to imitate one repetition of the process, explain clearly how to identify the outcomes of the chance process and what variable to measure. The next step is to perform many repetitions of the simulation. And the fourth and final step is to conclude. So use the results of your simulation to answer the question of interest. So we have 3 different experiments that we have done. We did the hiring discrimination. We haven't got to the 1 in 6 wins. And I don't believe, maybe we did talk about the distracted drivers. But we will go through each one of these and we'll talk about the state, the plan, the do, and the conclude, just so you have kind of an idea. So in the hiring discrimination, this is something that we did in the very beginning. It said, for your state, you would say, how likely is it that a fair lottery would result in 5 female and 3 male pilots being selected from an initial pool of 15 male and 10 female pilots? So the plan was make a special deck with 13 hearts plus any 2 diamonds and 10 spades. So we actually used cards that said male and female on it. But for this one, you let the red cards be the male pilots and the black cards be the female pilots. Shuffle and deal 8 cards, count the number of female pilots selected. The do for that is to have each student in the class do this 5 times, which is like what we did in class. And conclude, in 100 repetitions, 18 yielded 5 or more females, so about 18% of the time a fair lottery would choose at least 5 female pilots to become captains. We conclude that the company could have carried out a fair lottery. Distracted drivers. Is it plausible that by luck of the random assignment, 12 of the subjects were going to miss the rest area anyway, ended up in a cell phone group, while only 3 were assigned to passenger conversation group? So remove the ace of spades and 3 twos from a deck of 52 cards. So a jack, a queen, a king, and an ace would equal a missed rest area, and 2 through 10 would equal a stop at rest area. Shuffle well and deal 2 piles of 24 cards, the cell phone group and the passenger group. Record the number of drivers who missed the rest area in each group. The do would be have each pair of students repeat the process 10 times. And the conclude would be in 300 repetitions of the random assignment, there were only 2 times when 12 or more drivers who missed the rest area ended up being a cell phone group. That's less than 1% of the time. It doesn't seem plausible that the random assignment is the explanation for the difference between the groups. 1 in 6 wins, I know we for sure did not do. We are going to probably do this in class. So the state says, what's the probability that 3 of 7 people who buy a 20-ounce bottle of soda win a prize if each bottle has a 1 out of 6 chance of saying you're a winner? The plan says use a 6-sided die to determine the outcome for each person's bottle of soda. 6 equals wins a prize, 1 to 5 equals no prize. Roll the die 7 times, once for each person. Record whether 3 or more people win a prize, yes or no. The do says each student will perform 5 repetitions, and conclude says out of 125 total repetitions of the simulation, there were 15 times when 3 or more of the 7 people won a prize. So our estimate of the probability is 15 out of 125, or about 12%.